Alright, this is an introduction to the Plaited method, the Plaited algorithm that you would have learned about in class. This refers to the practice of sona, which is plural, which is the plural. Lusona is the singular for these sand drawings, or sand ideographs found amongst various people in eastern Angola. The people that we're focusing on most are the Chokwe, and there's lots of different ones, as you would have seen in class. We're looking at a couple different algorithms. This is the first one. So the way we talk about the sona that arise from this algorithm is as an outside perspective. They don't use this terminology when describing them, but so this is a description of what they're doing using our own terminology and our outside viewpoint. So what I want to show you is how to do it, how to make the designs that use this algorithm, and how to deduce some properties of the resulting sona. So I have some other videos after this which will go through a couple specific examples. So for starters, let's take a 3x3 grid, and one way to think about this algorithm is to imagine that the resulting design is a result of a ball bouncing around a room, say like a pool ball bouncing around the sides of a table, or to think of it as maybe a laser instead of a room full of mirrors. So it doesn't matter where you start here. All the lines are going to be at a 45 degree angle. So for example, I could start down here moving upwards, and the idea is that this line, if you imagine it to be the path of a ball on a pool table, when it gets to this corner, bounces off the wall, and it does a 180 degree turn. And then it continues unobstructed back to this corner. And in this case, we're back to where we started. And we haven't finished yet. Generally speaking, in all the diagrams, or all the sona, the dots are entirely enclosed. There are some examples where it's not the case. So we can do another one. I could start over here. Now imagine this is a pool ball. If it hits the wall at a 45, it reflects at a 45, and it bounces off this wall, and it bounces off this wall. Now I'm back to where I started again. And I have one more to do here. I can go down, get him bouncing around the corner. So this is a design, a 3x3 design, that would come about through using this particular algorithm, a method of accomplishing this design. And the idea, again, is that all the lines are at a 45 degree angle, and they are reflecting off some imaginary surface surrounding the dots. So in the corners, they reflect twice, making a 180. On the sides, it's a 90 degree angle. So we can try this on other grids. This one turns up several times amongst the corpus of sona. It'll be a turtle. And the practitioners, they were called Muposona. I need to review that. Here's a 3x4 grid. And so the first number always tells you the number of rows. So 3x4, 3 refers to the fact that there are 3 rows, and the 4 refers to the fact that there are 4 columns. So again, I can start moving up at some 45 degree angle. I could go there, or I could start here, it doesn't matter. And then I'm enclosing these dots. I'm bouncing around the diagram. I'm purposefully going slow here to give you a chance to follow along. And you'll notice that it goes around and closes these dots. If you think of the dots as forming lines, it's always to one side or the other of that line. Going into a corner here, I bounce twice. I come back out of it. Move across. Oops, I made a mistake there. I was talking too much. That should have gone under, actually. Let's do this again. All right, so where was I? I was up here. So there are the dots. I need to stay on just to their side, and then bouncing around. And this time you'll notice that the Lusona, or Lusona is singular, that the resulting Lusona needed only one curve. I didn't have to lift my pencil up. It is if I trace over this, there's only one curve, whereas in the 3x3 there were three separate curves. There was this one, there was this one, and then the last one. And we'll find there's a pretty easy relation for predicting. Excuse me. So let's try another one. So I could do, say, 4 by 4. This one's going to have more than one as well. So there's one. There's another. There's another. And there's the last. So that was a 4 by 4. So we had 4 curves in that one. We had 3 curves in this one. We had 1 curve on that one. And through all the examples you'll see, for the Plaited algorithm for a rectangular array, is the number of curves is the greatest common divisor of the grid dimensions. And you might remember the greatest common divisor is just the largest number that goes into any two numbers. So the largest number that goes into both 3 and 4 is 1. The largest number that goes into 3 and 3 is 3. The largest number that goes into 4 and 4 is 4. And this only holds for rectangular grids with the Plaited algorithm. Excuse me. Now the grid doesn't have to be rectangular, it just becomes a bit more complicated. We'll be looking at examples of this later. When you have, say, let's make something like this. So there are lots and lots of sona that are not rectangular, that have some other shape, and for a reason. All of these come with a parable or a story or an explanation. Remember from class that the men of the village would meet, have a meeting place, and they would take turns drawing one of these sona, and then afterwards explaining its significance, explaining the parts. And it might just be something like an animal. This is an antelope, or this is a tortoise. Or it might be that the dots and the lines represent something, people and paths through life, or physical paths from village to village. Or it could represent some abstract idea about serving your community, or God, or whatnot. So they're quite complicated. For the Plaited algorithm, which appears in all sorts of sona, the idea again is just think of this wall as a weird shaped pool table. And imagine the ball is moving around this pool table. So if I were to say start here, that ball again is going to bounce around corners. And every time it gets to the wall, it's going to bounce. And I want to stay on the right side of these 3 dots. Come to a wall. And then I want to make sure I don't cross this line. Right. And so this gives us a way of thinking about this algorithm. And mind you, we don't know. There haven't been enough studies really to know fully how they conceive of this practice. It's a dwindling practice. We're lucky to have about a half dozen really good studies from the Chokwe and also the Lukazi and the Ngangala peoples. They're all in a similar area, borders between Angola and Zaire. But these are almost always post-colonial, and there was a lot of distrust, of course, of these individuals, and so it's very difficult to get this information out of the people who knew it. And even in the 20s and 30s, which is one of the oldest studies of these, it was generally older folk, elders, who were the repository of information. So it's a dwindling, near extinct practice at the moment, and it's unfortunate we won't have a chance to really discuss with them the many different ways they think about these drawings. So anyway, this was definitely not a rectangle, and it only took 1 curve. And so we'd have a lot of work to do to figure out why this is, and to make some conjectures about whether they built this knowing that it would be monolinear, 1 curve, or whether that was important at all. In any case, this video is primarily concerned with just the execution of drawing these. How do you draw one of them? So we're going to talk about it as if it's a ball bouncing around a room, or a laser light bouncing around. And the results can be in just 1 curve, like this one and this one, or it can be quite a few different curves as these. So I hope this was helpful.